So this is the 14th class for the semester, vector calculus. So exactly halfway through when we're done today, 28 classes in the semester in CUNY. And the second exam, I think, will be in person 2 weeks from today on campus, covering functions of several variables, but to some extent also we'll have to include vector valued functions, but fundamentally it's on chapter 15 right now. And today's lesson is on the chain rule. So the chain rule in Calc 1 is a fundamental way to differentiate a composite function. So you have, let me try and draw it like this. So you have some function, let's say u is a function of x. So here we have our function f, and it sends a number x to some number u. But then we have another function g, which is a function of u, and y is some function g of u. So given a number u, the function g gives you this number y, which is g of u. U is f of x. And if you compose these two functions, if you take a number x, apply first f and then g, you have this composite function, g composed with f of x. All right. This is a composite function. Oops. Let's see if I can make this a little bit bigger and maybe easier to read. So we have this composite function, and the chain rule, so for a function of one variable, is the derivative of g composed with f with respect to x is the derivative of g with respect to u times the derivative of f with respect to x. Or if you think of this as u equals f of x, y equals g of u, dy dx is derivative of y with respect to u times du with respect to x. So if these were fractions, you would say, yes, you're just canceling the du's, but of course that's nonsense. And but this is the chain rule for a composite function of one variable. But now we're looking at functions of several variables, 2 or 3 variables. So now we have a situation where we have some domain and a point xy in R2, and we have some function that sends the point f of xy, has xy, to some point z, which is f of x comma y, right? This is a function of 2 variables. But it could be that you have that x is really a function of t, and y is a function of t. So on the number line, if you had a point t, you could send it to the point xy, which is really x of t, y of t. And then if you take t and it goes to this point in the plane, and then f sends a point in the plane to a number z, we have this composite function, which is z is a function f of x of t comma y of t. Right? And this is a complicated function, but it's a function of just one variable. You start with a number t, and you end up with a number z. And we want to know, for this composite function, dz dt, what is that equal to? And the chain rule says this is equal to the partial of z with respect to x times dx dt plus the partial of z with respect to y dy dt. So this is the chain rule in the case where you have a function f of two variables, but each of the variables come from functions x of t and y of t. Right? And the proof of this is not super hard, but it's harder than anything we would put into a 200 level math class. And it really requires a little bit more mathematical sophistication than we have available to us at this point. So that's the chain rule, which you have to know and love. And let's look at an example. So if z is f of x of t, y of t, dz dt, so this is a normary letter d, and these are the partial, the curly d's. Partial of f with respect to x, the partial derivative times the ordinary derivative dx dt, plus the partial of f with respect to y, dy dt. So suppose we have the function z, which is a function of x and y, which is the function x squared minus 3y squared plus 20. And x and y are both going to be functions of t. X of t is 2 cosine t, y of t is 2 sine t. So for every number t, it gets sent to a point with these coordinates. This is a point which is on the circle of radius 4. Right? So you have to recognize this as a point on this circle. So here's some point x of t, y of t. And then this point under the function f gets sent to some number z, which is equal to this. Right? So what is dz dt equal to? So by the chain rule, this is the partial of f with respect to x dx dt plus the partial of f with respect to y dy dt. This is z. What is the partial of z with respect to x? It's 2x. This is x. What is dx dt? Minus 2 sine t. What is the partial of f with respect to y? Minus 6y. What is the partial of y with respect to t? 2 cosine t. So we get minus 4x sine t minus 12y cosine t. So that is dz dt. And suppose we want to evaluate this at t equal to pi over 4. So when t is equal to pi over 4, what is x? X at pi over 4 is 2 cosine pi over 4. Cosine of pi over 4 is 1 over root 2, so that's root 2. Y at pi over 4 is 2 times the sine of pi over 4. This is again 1 over root 2, so this is also 2 root 2. So what do we get? We get dz dt is equal to minus 4x times the sine of t, sine over pi over 4, minus 12y root 2 times the cosine of pi over 4. Again, sine of pi over 4, cosine of pi over 4, these are 1 over root 2. So that cancels the root 2. So you get minus 4 minus 12 or minus 16. Okay. Now, if you want to know what does this look like geometrically, let me switch to the book where there's a very nice picture of this example. So let me share the screen for a second. So here's the problem I just did. Here's the function x squared minus 3y squared plus 20. If you look at the graph of this function, it's this hyperboloid. There's no way you can really do this by hand. You have to do it by computer, or for us, luckily, it's in the book. This is the graph of this function as a function of x and y. So in the xy plane, this is the graph. It's the surface in three-dimensional space. But now we're just looking at x equal to 2 cosine t and y equal to 2 sine t. That means x, as t goes from minus infinity to infinity, you're just going around the circle of radius 4. And that circle is some sort of curve on this hyperboloid. And we want to know what is the derivative of z with respect to t. And minus 16 is the value at this point. So at the point when t is pi over 4, that means you're right here, x and y are both root 2. You look at the point on when x is root 2 and y is root 2, z is minus 16. Here's the point, root 2, minus 16 on the surface. And the derivative of that point, of the function at that point, is this line with slope minus 16. Okay, good. Stop share, go back to our paper. Any questions about that? Again, visualizing these things is difficult. It's much harder than in first year calculus, where you're only looking at curves in the plane, things you can draw on a piece of paper. Now, of course, we don't have to have functions that involve functions of one variable and a function of two variables. You can have something more interesting, which is the following. You might have describe it like this. Z is a function of x and y. But it might be that x and y are both functions of two other variables, s and t. So x is really some function of s and t, and y is some function of s and t. So we have two functions of two variables, real value functions of two variables, and you can put them inside your f, and now we get a composite function z, which is f of x of s comma t, y of s comma t. So every pair in the plane st gets sent to x and y, which gets sent to z. So we have this somewhat more complicated composite function. And we want to know, so this is a function of two variables, and we can't talk about dz dt. We can only talk about the partial of z with respect to s and the partial of z with respect to t. And this chain rule tells us what these are. This is the partial of z with respect to x times the partial of x with respect to s, plus the partial of z with respect to y, partial of y with respect to s. And if we want dz dt, this is the partial of z with respect to x, partial of x with respect to t, plus the partial of z with respect to y, partial of y with respect to t. So this is the chain rule for the partial derivatives when you have a composite function of two variables. And again, these are perhaps complicated formulas to remember, but you have to learn them and you have to remember them. So let's look at an example. Suppose z, which is a function of x and y, is the function sine 2x cosine 3x. So for this function, of course, the partial of f with respect to with respect to x, it's like derivative of sine 2x, 2 cosine 2x cosine 3x plus sine 2x times the derivative of cosine 3x, which is minus 3 sine 3x. That's the partial of f with respect to x. And the partial of f, or z if you like, partial of z with respect to y. Oops, I'm sorry, I wrote this down wrong. Okay. I want to do the example in the book. So let's say f of xy is equal to sine 2x cosine 3y. So the partial of f with respect to x is 2 cosine 2x cosine 3y. And the partial, let me call this z, partial of z with respect to y is minus 3 sine 3y times the sine of 2x. So these are the two partial derivatives. But now, suppose x and y are themselves functions of s and t. X is equal to s plus t, and y is equal to s minus t. So the partial of x with respect to s is 1. Partial of x with respect, the partial of x with respect to t is 1. Partial of y with respect to s is 1. Partial of y with respect to t is minus 1. So if we want the partial of z with respect to s, it's the partial of z with respect to x partial s, plus partial z with respect to y partial s. Partial z with respect to x, here it is, 2 cosine 2x cosine 3y times the partial of x with respect to s, which is 1, plus the partial of z with respect to y, here it is, minus sine 2x sine 3y times the partial of y with respect to s, which is 1. So this is the partial derivative of x with respect to s. And if we want this, this makes a lot of sense, as a function of s and t, this is 2 cosine of 2x, x is s plus t, cosine of 3y, s minus t, minus the sine of 2x, or s plus t, times the sine of 3y, which is s minus t. So this somewhat long and complicated expression is the partial of z with respect to s. And you can calculate the partial of z with respect to t in a similar way. Okay. Any questions about this? This is just a technique in calculus, vector calculus, that you have to learn. Now, okay, so that's the chain rule. And there are a number of homework problems where you will just do exercises using the chain rule. The second bit of calculus of one variable, which carries over to functions of several variables, is implicit differentiation. So let's see, what's an example of how we did this in Calc 1? You had some function y, which might have been defined implicitly by some equation, 3x squared y cubed minus x e to the y equals 7. And you want to find, so this is some curve. The set of points that satisfy this is some complicated curve in the plane, and you want to find dy dx. So you would take the derivative of everything with respect to x. So by the product rule, the derivative of this first term with respect to x is 3 times 2x times y cubed plus 3x squared times the derivative of y cubed, which by the chain rule is 3y squared dy dx, minus the derivative of x e to the y, that's the derivative of x, which is 1, times e to the y, minus, you have to differentiate e to the y, which is x times ey prime e to the y equals the derivative of 7, which is 0, dy dx. So what I have is that I have two terms with a dy dx. This is 9x squared y squared minus x e to the y equals this and this. If I put this on the other side, equals e to the y minus 6x y cubed. And then you divide by this, and you found dy dx by what is called implicit differentiation. So this is something you learn in Calc 1, and you're not supposed to forget it. So there is an alternate form of this when you have, so here, what we have here is a function of the form 3x squared y cubed minus x e to the y minus 7. If we call that function capital F of x, y, we're looking at all the points where this is 0, and on that curve, I found dy dx, this divided by this. Let's see. What is, for this function, what is the partial of f with respect to x? And this is sometimes written as f sub x. If I take the partial of f with respect to x, I get 3 times 2x, 6xy cubed minus e to the y. And the partial of f with respect to y, or f sub y, is 3x squared times 3y squared, 9x squared y squared, minus x times the derivative of e to the y, which is e to the y. Now you'll notice something. This expression here is exactly f sub y. this expression is this. If I put a minus 6xy cubed minus e to the y, this is minus f sub x. So we could also have written the formula for dy dx by implicit differentiation as minus the partial of f with respect to x divided by the partial of f with respect to y. And so this seems to give an alternate formula, an alternate method for doing implicit differentiation. And we can justify that or explain that a little bit more as follows. Suppose we have a function f of x, y equal to 0. So this function is identically equal to 0. So all of its derivatives are 0. Let's use the chain rule to differentiate this with respect to x. So I could say the partial of f with respect to x is the partial of f with respect to x times the partial of x with respect to x, plus the partial of f with respect to y, partial of y with respect to x. And that's 0. And this is 1. So if I solve for dy dx is equal to minus this over this. That is, if you like, an alternate derivation of this formula. But in any case, this is a very useful formula to remember. It's an alternate way to get to do implicit differentiation. Let me see if there are any nice examples of this in the book, or otherwise I will just do it myself. Let's go back to more of these, of the chain rule. That's really the most useful thing. Suppose z is a function of x and y, and it's exactly the function x over y. But x and y are functions of s and t. X is s plus t squared, and y is s squared minus t. And I want to compute the first and second partial derivatives of f with respect to s. So by the chain rule, the partial of f with respect to s, or if you like, the partial of z with respect to s, is partial of z with respect to s, partial x with respect to s, plus the partial of z with respect to y, partial of y with respect to s. Okay, that's the chain rule. And we have to calculate these things. The partial of z with respect to x is 1 over y. Partial of x with respect to s is 1. Partial of z with respect to y is minus x over y squared. Partial of y with respect to s is 2s. So the partial of z with respect to s is 1 over y minus 2xs over y squared. Right? Suppose we want the second partial derivative of z with respect to s. So this is my function, and I want to differentiate this with respect to s. So let's see, what should I do? So this is partial of z with respect to x, partial of x with respect to s, plus partial of z with respect to y, partial of y with respect to s. That's the partial of z with respect to s. And if I want to differentiate this again, that's by the product rule. That's the partial of z with respect to x differentiated with respect to s times x sub s, plus the partial of z with respect to x, partial of x with respect to s differentiated again with respect to s, plus the partial of z with respect to y differentiated with respect to s, times the partial of y with respect to s differentiated again with respect to s. And this gets more and more complicated, but that's just the way it is. What is the partial of z with respect to x differentiated with respect to s? So again, now we're using the chain rule here. Z sub x is a function of x and y are functions of s and t. So if I differentiate z sub x with respect to s, that's the partial of z sub x differentiated with respect to x times x differentiated with respect to x, s, plus the partial of z with respect to x differentiated with respect to y times the partial of y with respect to s. I differentiate this, plus, so that's all this times x sub s, plus zx with respect to s, and then x differentiated with sub s differentiated with respect to s. So that is x differentiated twice with respect to s. And then I have the derivative of might need a bigger piece of paper for this. Z sub SS. Right. Let me just start this on a clean piece of paper. It's going to take up a lot of space. So I have Z is a function of X and Y. It's equal to X over Y. And X is S plus T squared, and Y is S squared minus T. And what are the second partial derivatives? You can have the partial, you can differentiate Z twice with respect to S. I'll call that Z sub SS. You can differentiate Z with respect to S, and then with respect to T, I'll call that Z sub ST. You can differentiate Z twice with respect to T, I'll call that Z sub TT. Now you can also differentiate in the opposite order. I could take Z, I could differentiate it with respect to T, and then differentiate it with respect to S, and I could call that z sub ts, but there's a theorem that says if the second partials are derivative, are continuous, it doesn't matter what order you differentiate in, that the derivative of z with respect to first s and then t is the same as the derivative of z with respect to t and first s. So these two quantities are exactly the same. So let's take a look. So the book uses a kind of useful formula here. If you're differentiating some function with respect to s, that's that function differentiated with respect to x times the derivative of x with respect to s, plus that function differentiated with respect to y times the derivative of y with respect to s. And a similar formula holds for differentiating something with respect to t. Is that differentiated with respect to x times the partial of x with respect to t, plus that same thing differentiated with respect to y times the partial of y with respect to t. And these are the two formulae for the derivative of a function of two variables, where each variable is a function of two other variables. So let's try to compute the second derivative of z with respect to s. So the derivative of z with respect to s, and then you differentiate with respect to s. What's the derivative of z sub s with respect to s? That's equal to what is z sub s? Z sub s is z sub x, x sub s, plus z sub y, y sub s. That's this first derivative, the first partial of z with respect to s. And then we're differentiating that with respect to s. And that is the sum of these two second partials with respect to s. So let's see, so we're differentiating with respect to s. So it's this differentiated with respect to x. So this is equal to zx, zs, zx, xs, plus zy, ys, differentiated with respect to s times x sub s, plus this thing differentiated with respect to y, y sub s, z sub x, x sub s, plus z sub y, y sub s. When I differentiate this with respect to x, if I differentiate this, with respect to s, this is let me just, if I differentiate this with respect to s, that's the same as zx, xs, differentiated with respect to s, plus zy, ys, differentiated with respect to s. That's the derivative of the sum of two functions is the sum of the derivatives. So if I differentiate this, what do I get? I get z sub x S x sub s plus z sub x sub ss. That's just the product rule. And if I apply the product rule to this, I get z sub y s y sub s plus y sub ss. And then if I apply the chain rule to this, let's see what I get. I get z sub x sub s plus z sub x y sub s. Plus z sub x sub ss. I differentiate this with respect to y by the chain rule, with respect to s by the chain rule. I get z sub y x sub s plus z sub y sub s plus this term y sub ss. So I get 1, 2, 3, 4, 5. I get 6 terms. And zxy and zyx are the same. That's definitely true. I have a zxy y sub s and a zys x sub s. So let's see, what do I have here? I have zxx it's this times x sub s and this times y sub s. So instead of my trying to write this out painfully, let me just show you what it looks like in the text, because I'm trying to follow the example in the text. So here is my function. Let me just go back one page. I have the function z is x over y. It's a function of 2 variables, but x and y are each functions of 2 variables, s and t. X is s plus t squared and y is s squared minus t. So this is the partial of z with respect to s and the partial of z with respect to t by the chain rule. If I want to differentiate this again with respect to s, it's this with respect to s. And I differentiate this with respect to s, I get this. And if I differentiate this with respect to s, I get this. And I get this. Well, I get some complicated expression which simplifies and simplifies and simplifies, and just a lot of work. So I'm not sure what to say about this. It's simply that you have to start to look at the examples very carefully in the text and to develop the technique. So I'll give you a chance to work on some of these over the next 2 days, and I'll do a couple of exercises first thing on Wednesday. But let's move ahead to something which is less directly computational and more geometrically interesting, which are the directional derivatives. So this is section 15.5 on directional derivatives, and maybe I'll just follow in the text so the pictures will look very nice. So if you have a function of two variables, so for every x, y in the plane, the graph is the surface in three-dimensional space. And we looked at the partial derivatives of the function with respect to x and y. So that's the rate of change as you move along. If you were to like slice through the surface by a plane perpendicular to the y-axis, so parallel to the xz plane, that would trace out a curve on the surface, and the partial of f with respect to x is the slope of the tangent to the curve at a point, or the rate of change of the function. And if you cut the surface with the plane perpendicular to the x-axis, that is parallel to the yz plane, you get a curve parallel to the yz plane, and the derivative of that is the partial derivative of your function with respect to y. So if I take my surface and I intersect with the plane perpendicular to the x or the y axes, I get a curve where the tangent line at any point is given by the partial derivatives. But I can cut my surface with any plane. It doesn't have to be perpendicular to the x or the y axes. I can take any plane. And when you cut the surface, you cut out some curve, and it is changing as a function of your variables. And you want to know something about the tangent line or the rate of change. That's the same as asking, how do you find the partial derivative of your function in any direction, not just in the x and the y direction? And those are what are called the directional derivatives, as you see here. So on my surface, if you take a point AB in the plane, here's the surface and here's the point AB, and the z coordinate is f of AB. That's my surface. And I want to take some direction u in the plane. And from this point in the plane, I go in the direction u. And I want to find some derivative of my function in that direction. And the natural way to define that would be by this formula. If u is a vector with coordinates u1, u2, and you start at the point AB and you move a little bit in the direction of u, then your point AB moves to a plus hu1 and b plus hu2. So if you take the value of the function at this point, minus f of AB, and divide by h, and to make things sort of unambiguous, we take u to be a unit vector, a vector of length 1, because we only care about the direction. The magnitude is irrelevant. So you take the vector u, it's not 0, divide by its length, and you get a unit vector. So here we have this limit, if it exists, is exactly what we would call the directional derivative at the point AB in the direction of u. And a kind of a picture is this. You have to stare at these things for a while. Here's the xy plane. Here is the point AB. Here's the direction u. On my surface, if I were to take a plane through the point AB in the direction u perpendicular to the xy plane, it cuts out a curve on the surface, and that curve is a function of, let's say, some variable t, and I want to know what is the derivative of that. And so this is exactly the definition of the directional derivative at a point AB. You take a unit vector u in the xy plane, and this formula, the limit, if it exists, is called the directional derivative of f with respect to u. Right? That's what it is. So what is a way to figure out the directional derivative? Really, it's really worth looking at this picture a lot. Here we go. So let's say we take the line through the point AB in the direction of U. What is the equation of this line? Well, in chapter 1, we learned, or the first chapter in this course, we learned how to find the equation of a line through a point in the direction U. Right? So let's see whether, so if you're going in the direction U, if you can parameterize the line by x equals a plus su1 and b equals y equals b plus su2. So if you take this formula and you plug it into the definition of the directional derivative, you get a function of s. So this is function along the line. And so let me do this on a piece of paper, perhaps, and maybe it's a little bit easier to see. So I want to find the directional derivative. So we have f is a function of x and y. So, and we have a point in the plane AB, and we take a unit vector u. So this is a unit vector. So u has coordinates that say u1, u2. So what is the equation of the line in the plane through the point AB and parallel to u? So if you go in this direction, a small amount in the direction of u, this would be, let's say, a plus s times u1, b plus s times u2, right? So you can think of this as like, here we have su. Here we have the point AB. And if we go a distance su, that's AB plus su1, u2. That's exactly this point. And if I think of the function g of s to be equal to f evaluated at a plus su1 and b plus su2, I want to say that the directional derivative is dg ds. What is that? That's, if I take the function f, that's like the partial derivative of f with respect to s. So that's the derivative with respect to s of f of a plus su1, b plus su2. I think of that as a directional derivative with respect to s of the function f of x, y, where x is a plus su1 and y is b plus su2. So I apply the chain rule to this. This is the partial of f with respect to x, dx ds, plus the partial of f with respect to y, dy ds. That's the partial of f with respect to x, dx ds is u1, and the partial of f with respect to y times dy ds, which is u2. That's what it is. And you can think of this as, if I had the vector partial f with respect to x, partial f with respect to y, I'm taking the dot product of that with u1, u2. And that is the fundamental formula for the directional derivative of a function of two variables in the direction of the line, in the direction of the vector u. So let me just copy that down again because I'm going to use it in a second. So I have f is a function differentiable at the point a, b, and I have a unit vector u with coordinates u1, u2. The directional derivative in the direction u of the function f evaluated at ab is the inner product or the dot product of the partial of f with respect to x at ab, partial of f with respect to y at ab, dot product with u. That's the directional derivative. So for example, suppose I have the function z equal f of x, y, which is a fourth x squared plus 2y squared plus 2. So this is what is called a paraboloid. And suppose I want to go in the direction of the vector u, 1 over root 2, 1 over root 2. So this is a unit vector. And suppose I take the point P naught with coordinates 3, 2. So the directional derivative of this function f in the direction u at the point 3, 2, I take the dot product of the partial of f with respect to x, partial of f with respect to x, make a little table here. So this is f. Partial of f with respect to x is 1/4 times 2x or x over 2. So the partial of f with respect to x at the point 3, 2 is 3/2. The partial of f with respect to y is 1/4 times 2 times 2y, which is y. So the partial of f with respect to y at the point 3, 2 is 2. So the derivative of f in the direction u at the point 3, 2 is the dot product of fx, fy. That's 3/2 2 dot product with u1, u2, 1 over root 2, comma 1 over root 2. So that's 3/2 times 1 over root 2 plus 2 times 1 over root 2 is 1 over root 2 times 3/2 plus 2, which is 7 over 2 root 2. And that's the directional derivative. This vector is very important and has a name. It's called the gradient. So the gradient of f, which is usually written with the upside down Greek letter delta of f at xy, it's the vector whose coordinates are the partial of f with respect to x and the partial of f with respect to y, or using ij notation, partial of f with respect to xi plus the partial of f with respect to yj. And so we can also say the directional derivative of u, of f in the direction of u at any point xy, it's the dot product of the gradient of f with the vector u. Let me just do an example or two. So the gradient of f with respect to x and y is the partial of f with respect to x times I plus the partial of f with respect to y and j. So suppose f of x, y is equal to x squared plus 2xy minus y cubed. So the partial of f with respect to x is 2x plus 2y. Partial of f with respect to y is 2x minus 3y squared. So the gradient of f is equal to 2x plus 2y, or 2 times x plus yi, plus 2x minus 3y squared j. And if I wanted the gradient, for example, at the point 3, 2, when x is 3 and y is 2, this is 5, I get 10i, 2x is 6, minus 3 times 4 is 12, minus 2j. Oops, sorry. X is 3, 3 times 2 is 6, y is 2, 2 squared is 4, 12, 6 minus 12 is minus 6. Better to get it right. Now, this formula that the direction of u, the directional derivative of f and the direction of u, is the gradient of f dot product with u, tells us a lot geometrically about the gradient, because we know that the dot product of two vectors is the length of the vectors times the cosine of the angle between them. But this is a unit vector. The length of this vector is 1. So this is equal to the gradient, the absolute value of f of x, y, times the cosine of theta. So here we have the gradient, and here we have u, and this is the angle between them. Now, cosine theta goes from -1 to +1. So this is largest when this is equal to 1, and it's smallest when it's equal to -1. So the maximum value of the directional derivative of f is at theta equals 0. That is, when we choose the direction exactly in the direction of the gradient. And the minimum is when this is -1, or theta is pi. So the rate of greatest increase of f of x, y is in the direction of the gradient of f. That's what we would call the steepest ascent. And where it is decreasing most rapidly, or the steepest descent, is in the direction of minus the gradient. So the gradient vector of a function at a point tells you the direction at which it is increasing most rapidly. And I should observe that this carries over to functions of 3 variables. Indeed, for functions of any number of variables. So if we have some function w of 3 variables, x, y, and z, the gradient of f is the partial of f with respect to xi plus the partial of f with respect to yj plus the partial of f with respect to z, k. And the directional derivative of f in the direction of u in 3 dimensions is still the dot product of the gradient of f with u. So in 3 variables x, y, and z, you have the direction of steepest ascent is in the direction of the gradient, and the direction of steepest descent is in the opposite direction, minus the gradient. So this is all new and complicated. You really have to spend a lot of time studying the textbook, looking at the pictures over and over and over again, as much as you can. And there is always what is called a level curve. So if you have a function z equals f of x, y, the level curve z equals some number. Let's see what letter does the book like to use for this. Or all the points f of x, y equals z naught. These are all the points x, y in the plane where f of x, y has this fixed value z naught. So for example, if you had a paraboloid, if you look at a level curve, it would be some cross section through this paraboloid. It would be a circle or an ellipse. That would be an example of a level curve. All the points which are a certain height above or below the xy plane. That's the level curve. And along this level curve, the value of the function doesn't change. So if you were to take the directional derivative along this curve at this point, it would be 0. Of course, it's a constant along that curve. And it will be perpendicular, and the derivative will be perpendicular to the gradient. So I'm going to review all this again on Wednesday, but really this is, we've reached the point in the course where things get a little bit more sophisticated, a little more complicated. And it takes a lot of time to work through the material in the text and understand it. And I encourage you to come to the problem sessions I have. They're usually underpopulated. But that means there's plenty of time, plenty of opportunity for you to ask questions about things that you find confusing or about problems that you had difficulty doing. And the more you do that, the better. Okay.
Excuse me, Professor.
Yeah,
So just to make sure, the second exam is on the 7th.
2 weeks from today.
Okay, and I have 2 more questions. I have a first, like for the exam, will we be able to like bring like notes or anything like that?
Yes,
Okay, so we can have handwritten notes. Okay.
I believe so, yes. But it's going to be an in-person written exam. It's not a Pearson exam.
Okay, so since it's not a Pearson exam, will we have like a study guide on like how like the problems are gonna be formulated? Because like I know on Pearson, right, they have like a certain way that the questions are formatted and the way that you answer them. Like, will
Yeah,
we have like a
I
study
will
guide?
send out a kind of a review sheet, but in the exact format of an exam, of the exam.
Okay, thank you, Professor. Because like with Pearson, like I looked at the chain rule assignment, right? And what you went over in the questions that you did is like looks nothing like the stuff that they have. They have like for their assignment they have like a tree diagram or something like that, which is
Right,
kind of not what we just reviewed.
right. Well, I mean, if you look at the text, you'll see tree diagrams, but it's more important, I think, if I give you a function that you actually know how to take the partial derivative, or you actually know how to use the chain rule to get a partial derivative.
Yeah.
And that, yes. And the
Mhm.
tree is just, a kind of a way maybe to break down the function into components, but you still need to solve the problem.
Okay. All right, thank you, Professor.
Okay. Other questions? Anything? All right, then I think I will quit for the day. Again, I remind you, there's an office hour. There are office hours certainly every week, Monday and Wednesday at 1 and Fridays at 11. And I set up other hours by appointment if you can't make one of those and you send me an email. So there are plenty of opportunities to ask questions. Okay, I'll be back on Wednesday. Bye.